The morning of February 16th, 1943. Sbeitla, Tunisia. The Panzer IV sat abandoned beside a rutted dirt road, its engine cold, its crew long gone. Sergeant Mike Harrison of the 740th Tank Battalion approached cautiously, Thompson's submachine gun ready, expecting ambush or booby traps. Instead, he found silence. The German tank had been disabled not by American guns, but by something far more mundane. Mechanical failure during retreat. The tracks were intact. The armour showed no penetrations. The 75mm gun pointed uselessly at empty desert. This tank had simply stopped working at the worst possible moment for its crew, forcing them to abandon it and flee on foot as American forces closed in. Harrison radioed for recovery crews and ordnance specialists. Within hours, technical intelligence teams descended on the abandoned Panzer like engineers, examining an alien spacecraft. They photographed every angle, measured every component, documented construction techniques with meticulous German precision, turned back upon German engineering itself. But it was when American mechanics tried to understand the basic maintenance requirements that the real education began. The transmission had failed. Standard procedure would be to replace it and get the tank operational again for evaluation. The Americans assumed this would take a few hours, maybe half a day at most. After all, on a Sherman, swapping out the entire powertrain took a trained crew about 2 hours with proper equipment. The Panzer IV used a similar front-mounted transmission layout. How different could it be? The answer would reshape American understanding of why German armour, despite its technical sophistication and fearsome reputation, kept losing battles to numerically superior Allied forces that fielded mechanically simpler equipment. The mathematics of armoured warfare were about to be rewritten, not through superior firepower or thicker armour, but through a principle the Germans had never prioritized above all else: automotive serviceability that ordinary soldiers could actually perform under field conditions without specialized training, exotic tools, or engineering degrees. The Panzer IV had served as Germany's primary medium tank since 1939. By 1943, it had evolved through multiple variants, each attempting to keep pace with increasingly formidable Allied armour. The Ausf G model, which began production in May 1942, represented the most numerous version. Germany built 1,687 Ausf G variants through June 1943, more than any other Panzer IV model. These tanks featured the long 75mm KOK-40L 43 gun, a significant improvement over earlier short-barreled versions. This weapon could penetrate 80mm of armour at 1,000 metres range, making it effective against any Allied tank in North Africa during early 1943. The Panzer IV weighed approximately 25 tons in combat configuration. Its Maybach HL 120 TRM engine produced 300 horsepower, providing adequate mobility across the desert terrain of North Africa. The tank carried a crew of 5: commander, gunner, loader, driver, and radio operator. Its combat record was impressive. During Operation Frühlingswind in February 1943, Panzer IVs destroyed 97 American Sherman tanks in just 2 days. German tank commanders praised the long 75mm gun's effectiveness. Reports from the 5th Panzer Division noted that Soviet tanks ranging from the lightly armoured T-26 to the heavily protected KV-1 could be destroyed at ranges between 1,200 and 1,600 metres, with only a few rounds. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching. From today, but raw combat performance told only part of the story. American ordnance officers examining abandoned and captured Panzer IVs in Tunisia during spring 1943 began documenting a different picture. One that revealed fundamental differences in design philosophy between German and American approaches to armoured vehicle development. Technical intelligence teams set up evaluation facilities wherever sufficient numbers of captured tanks accumulated. They measured, photographed, and systematically disassembled German vehicles to understand their strengths and weaknesses. The transmission examination began with basic disassembly procedures. American mechanics familiar with Sherman maintenance approached the Panzer IV, expecting similar simplicity. The Sherman's powertrain, consisting of transmission, differential, and final drives, could be removed as a single integrated unit. A trained crew could unbolt the entire assembly from inside the hull, use a wrecker or armored recovery vehicle to lift it out through the front, and install a replacement unit. Total time for a complete powertrain swap in field conditions. Approximately 2 hours with proper equipment and a well-trained crew. The Panzer IV's front-mounted transmission seemed to promise similar accessibility. Located in the bow of the tank, directly behind the frontal armor plate, the transmission connected to the engine via a long drive shaft running beneath the turret basket. This layout, shared with the Sherman, suggested straightforward maintenance procedures. American mechanics opened the front transmission access hatches, expecting to find a relatively simple removal process. Instead, they discovered a maintenance nightmare that would require an entire day of work, specialized tools, and skills far beyond what ordinary tank crews possessed. The transmission itself was a complex mechanism. The SSG 75 gearbox provided 6 forward speeds and 1 reverse, representing sophisticated German engineering. Unlike the Sherman's synchronized transmission that eliminated the need for double clutching in most gears, the Panzer IV required careful rev matching and precise clutch control. German tank drivers received extensive training in proper shifting techniques. Aggressive gear changes or improper clutch use could damage the transmission, a chronic problem that plagued Panzer units throughout the war. But the real shock came when American mechanics tried to remove the failed transmission for replacement. Step 1 required draining all fluids. Not just transmission oil, but also engine coolant, as the cooling system ran through passages that had to be disconnected. This alone took 30 minutes of careful work to avoid spills that would contaminate the crew compartment. Step 2 involved disconnecting the drive shaft. On a Sherman, this was a straightforward bolt removal. On the Panzer IV, the drive shaft connected through a complex universal joint system that required precise alignment during reassembly. Getting it wrong would cause vibration, premature wear, and eventual failure. Disconnecting it properly took another 30 minutes. Step 3 revealed the true nightmare. The transmission didn't simply bolt to the hull like the Sherman's integrated powertrain unit. Instead, it was integrated into the front hull structure itself, surrounded by armor plates and structural members that couldn't be removed without essentially disassembling the entire bow of the tank. The steering brake mechanisms, mounted on either side of the transmission, had to be disconnected first. Each brake mechanism included multiple linkages, hydraulic lines, and adjustment points. Removing these without losing critical small parts or damaging seals required careful documentation and organization that field conditions rarely provided. Step 4 involved the final drive units. Unlike Sherman final drives that could be serviced independently, the Panzer IV's final drives integrated with the transmission housing in ways that required removing them before the transmission could be extracted. Each final drive weighed approximately 50 kilograms and required careful handling to avoid damage to the gear teeth. Removing both final drives added another 2 hours to the process, assuming no stripped bolts or corroded fittings complicated the work. Step 5, actually removing the transmission, required specialized lifting equipment. The transmission alone weighed over 200 kilograms, nearly half a ton. It couldn't be manhandled out by brute force. German maintenance units used specialized jacks and hoists designed specifically for this purpose. American mechanics examining captured tanks in Tunisia often lacked these specialized tools, forcing them to improvise with whatever equipment they had available. Getting the transmission out without damaging surrounding components took extreme care and patience. Step 6 involved dealing with all the ancillary systems, electrical connections for various sensors and switches, mechanical linkages for gear selection and clutch operation, hydraulic lines for the steering brakes. Each system had to be carefully disconnected, labeled, and protected during removal. German technical manuals provided detailed procedures, but these manuals were written in German and assumed the mechanic had completed specialized training in panzer maintenance. American mechanics, working through translators and learning on the fly, faced constant challenges. The entire removal process, performed by experienced American mechanics who had done this type of work before on captured vehicles, took approximately 8 to 10 hours, and that was just removal. Installing a replacement transmission and reassembling everything properly took just as long. Accounting for alignment checks, fluid refills, and post-installation testing, a complete Panzer IV transmission replacement required 16 to 20 hours of work by trained mechanics with proper tools and equipment. Compare that to the Sherman's 2-hour powertrain swap, and the disparity became obvious. A broken transmission could keep a Panzer IV out of action for days. The same failure on a Sherman meant hours, not days, before the tank returned to combat operations. American ordnance officers documented these findings in detailed technical reports that circulated through Army maintenance commands. The reports noted that German design philosophy prioritized performance specifications over maintainability. The Panzer IV transmission, while sophisticated in its engineering, required specialized knowledge to service properly. German tank crews received extensive training, but even experienced crews couldn't perform major repairs without proper equipment and workspace. Field maintenance capabilities, so critical in sustained combat operations, were severely limited by design choices that looked impressive on paper but created nightmares in practice. The comparison with Sherman maintenance philosophy couldn't have been more stark. American automotive engineers who designed the Sherman came from an industry with decades of experience building vehicles that ordinary people could maintain. The Ford Motor Company, General Motors, Chrysler, and other manufacturers had learned through harsh economic competition that reliability and serviceability determined success in the civilian automotive market. These lessons transferred directly to military vehicle design. The Sherman incorporated commercial automotive components wherever possible. The transmission came from multiple manufacturers, Caterpillar, Buick, Ford, all building to identical specifications with fully interchangeable parts. A transmission from one manufacturer could replace a unit from another without modification or special fitting. This standardization, routine in American automotive production, was largely theoretical in German manufacturing, where each factory introduced subtle variations. The Sherman transmission featured herringbone-cut gears that distributed stress across multiple teeth simultaneously. This design, standard in American heavy-duty transmissions since the 1930s, provided exceptional durability with minimal precision requirements. German engineers knew about herringbone gears, but considered them too difficult to mass-produce, given Germany's industrial capabilities and workforce training. The Americans had been manufacturing them by the thousands for years in civilian trucks and tractors. When the Sherman needed a transmission, designers simply adapted proven commercial technology rather than creating something entirely new. The synchronized manual transmission in the Sherman, with synchromesh in 2nd through 5th gears, made driving nearly as easy as operating a civilian automobile. Drivers with basic automotive experience, commonplace among young Americans in the 1940s, could operate a Sherman with minimal additional training. The Panzer IV's non-synchronized transmission required double clutching and careful throttle management, skills that took considerable time to master. More importantly, improper shifting technique could damage German transmissions in ways that Sherman transmissions simply shrugged off. American tanks were designed to be operated and maintained by ordinary soldiers with ordinary skills. German tanks assumed highly trained specialists would be available. The cooling system differences highlighted another philosophical divide. The Sherman's cooling system, while simple in design, proved highly effective across temperature ranges from desert heat to winter cold. The air filtration handled sand without the frequent clogging that plagued German tanks in North Africa. When maintenance was required, the systems were accessible and used standard tools. The Panzer IV's cooling system, more complex and theoretically more efficient, required specialized procedures, even for routine service. Coolant passages integrated into the transmission housing meant that transmission work required cooling system work, and vice versa. Every job became more complicated than it needed to be. American examination of captured Panzer IVs revealed quality manufacturing and precision engineering. The tanks were well built using excellent materials, but they were built to standards that made sense only if you had unlimited access to specialized tools, trained mechanics, and generous time for maintenance. German panzer divisions in North Africa rarely enjoyed such luxuries. Supply lines stretched across the Mediterranean faced constant interdiction by Allied air and naval forces. Spare parts arrived irregularly. Specialized maintenance equipment was often unavailable. Trained mechanics became casualties at the same rate as other soldiers, and couldn't be easily replaced with personnel having the required specialized skills. Field commanders reported the consequences. Panzer units frequently showed operational readiness rates below 50%. At any given time, more than half the tanks in a unit were deadlined, awaiting repair or parts. Some breakdowns were combat damage that no amount of good design could prevent, but many were mechanical failures that could have been avoided with better maintainability. Transmissions failed after relatively short service lives. Final drives broke under loads they should have handled. Cooling systems developed leaks that were difficult to repair in field conditions. Each failure meant days or weeks of a tank sitting useless while mechanics struggled with repairs that required time and equipment they didn't have. Meanwhile, Sherman units maintained operational readiness above 70% throughout the North African campaign. Tanks broke down, certainly. Combat damage occurred regularly, but Sherman mechanics could perform repairs quickly using skills they already possessed from civilian, automotive experience. Parts were available in quantities German units could only dream about. When a Sherman needed major work beyond field capabilities, it went to a maintenance depot for rebuild. When a Panzer needed similar work, it often sat abandoned because recovery wasn't feasible, and proper repair facilities didn't exist within reasonable distance. The strategic implications became clear to American military planners examining the data from Tunisia. Germany's industrial capacity couldn't match Allied production. German factories built 8,553 Panzer IVs of all variants during the entire war. American factories built 49,324 Sherman tanks during the same period. Britain added thousands more. The Soviet Union received over 4,000 diesel Sherman variants through Lend-Lease. Every theatre where Sherman served confirmed that properly maintained tanks kept running under conditions that would disable or destroy German equivalents. But the numerical advantage, while significant, wasn't the whole story. The real advantage was that American tanks could be maintained by ordinary soldiers using ordinary tools under field conditions. A battalion maintenance section with basic equipment could keep Sherman tanks operational through extended combat operations. A comparable German unit struggled to maintain half their vehicles operational, even when parts were available. This wasn't incompetence. German mechanics were skilled and dedicated. The problem was systemic. German tanks required levels of specialized support that simply couldn't be sustained in combat conditions. Spring 1943 brought additional Panzer IV captures as Allied forces drove Axis armies into an ever-shrinking pocket in northern Tunisia. Each captured tank underwent similar examination by American technical intelligence teams. The findings were consistent across all vehicles examined. Excellent combat capabilities when the tanks actually worked. Sophisticated engineering that impressed American engineers, but maintenance requirements that exceeded what combat conditions could support. The transmission problems were merely the most dramatic example of a broader pattern. Every major system on the Panzer IV showed similar characteristics, well engineered in isolation but difficult to service in practice. The engine, a Maybach HL 120 TRM producing 300 horsepower, was a fine piece of engineering, but it required constant adjustment of valve clearances, ignition timing, and carburetor settings. Sherman engines, whether the Continental Radial, the Ford GAA Vate, or the GM twin diesel, needed far less frequent adjustment and ran reliably with minimal maintenance. The suspension system on the Panzer IV used leaf springs, actually simpler than the Sherman's vertical volute spring system. But access to suspension components for service required removing side skirts and track sections, a time-consuming process. Sherman bogies could be serviced relatively easily from outside the vehicle. Track replacement on both vehicles required similar effort, but the Sherman's design made it possible to change tracks using just the crew. The Panzer IV often needed additional personnel and equipment for the same job. Every comparison revealed the same pattern. German engineering pursued theoretical optimization in individual components. American engineering pursued practical optimization of the complete system with emphasis on what soldiers could actually accomplish in field conditions. One approach produced tanks with impressive specifications. The other produced tanks that actually worked reliably in the chaos of combat operations. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By May 1943, when the last Axis forces in North Africa surrendered, American ordnance had accumulated extensive data on German armoured vehicles. The reports documented strengths and weaknesses in exhaustive technical detail. Combat performance, armour protection, firepower, mobility, all received thorough analysis. But the maintenance findings carried special weight because they explained a paradox that had puzzled American commanders. How could German tanks with superior guns and heavier armour keep losing to numerically superior but individually inferior Allied armour? The answer wasn't purely numerical. Yes, Allied production vastly exceeded German output. Yes, Allied logistics could deliver overwhelming quantities of supplies, including replacement vehicles. But the fundamental issue was that German tanks couldn't maintain sustained operations because their maintenance requirements exceeded what combat conditions would support. A Panzer unit at 50% operational readiness could generate only half the combat power of its theoretical strength. A Sherman unit at 75% operational readiness could generate 3/4 of its strength consistently over time. In armoured warfare, as in most military operations, sustained combat power mattered more than momentary capability. A tank that could destroy any enemy vehicle at 2,000 meters range was worthless if it broke down 500 meters short of the battlefield. A tank with mediocre armor penetration but absolute reliability to reach the fight and complete the mission was infinitely more valuable. German tank designers pursued the former. American designers, learning from decades of commercial automotive experience, pursued the latter. The captured Panzer IVs in Tunisia provided object lessons that influenced American tank development for decades. The reports emphasized that combat effectiveness depended not just on specifications, but on sustained operational capability. Reliability wasn't a secondary consideration. It was foundational. Maintainability wasn't a convenience. It was a combat requirement. These principles, proven through examination of enemy equipment and confirmed by combat experience, shaped post-war American armored vehicle design. The M48 Patton tank, developed in the late 1940s and introduced in 1952, incorporated lessons learned from examining German vehicles. The design emphasized reliability and maintainability alongside combat performance. The M60 tank that followed showed similar priorities. Even the Monet Abrams, developed in the 1970s and introduced in 1980, reflected these enduring principles. American tank designers never forgot the lesson learned from examining abandoned Panzer IVs in the Tunisian desert. The most sophisticated engineering in the world was worthless if ordinary soldiers couldn't maintain it under combat conditions. The specific Panzer IVs captured in Tunisia during spring 1943 eventually made their way to Aberdeen Proving Ground in Maryland, where they underwent even more exhaustive testing. Aberdeen specialized in detailed automotive trials that stressed every system to failure, documenting exactly how much abuse vehicles could withstand before breakdowns occurred. The Panzer IVs performed these tests under controlled conditions that German units in the field could never hope to match. Proper tools, unlimited time, trained specialists. Even under these ideal circumstances, the maintenance requirements remained daunting. Test engineers documented that transmission removal, even by specialists familiar with the procedure and equipped with proper tools, required a minimum of 6 hours. Installation and reassembly took another 6 hours. Total time for a transmission replacement under optimal conditions, 12 hours. Double that for field conditions with less than perfect equipment, and you approach 24 hours. An entire day lost to repair work that Sherman crews accomplished in 2 hours. The final drives presented similar challenges. Sherman final drives, built using herringbone gears that rarely failed, needed little maintenance. When they did require service, the entire unit could be removed and replaced relatively quickly. Panzer IV final drives used straight-cut gears that wore faster and failed more frequently. When replacement became necessary, the procedure required removing the transmission first, in many cases, compounding the work required. German field reports documented final drive failures as one of the most common causes of vehicle immobilization throughout the war. Aberdeen testing confirmed what had been observed in Tunisia. German tanks represented superb engineering applied to create sophisticated machines that required extraordinary support to maintain in operation. American tanks represented sound automotive engineering, applied to create practical machines that ordinary soldiers could keep running under adverse conditions. In a war of industrial attrition where sustained operational capability determined victory, the American approach proved decisively superior. The lessons learned from examining captured Panzer IVs influenced more than just tank design. American military doctrine evolved to emphasize integrated logistics, recognizing that combat power depended on maintenance support as much as firepower and protection. Training programs expanded to ensure soldiers possessed practical mechanical skills. Supply systems developed to ensure parts availability rather than assuming units could operate with minimal resupply. Every aspect of American armored warfare doctrine reflected understanding gained partly through examining how German approaches failed in practice. German veterans interviewed after the war frequently mentioned maintenance problems as one of the most frustrating aspects of fighting in panzer units. They praised German tanks' combat capabilities, while acknowledging that breakdowns often prevented them from exploiting those capabilities. Many noted that captured Sherman tanks, pressed into service by desperate German units, proved remarkably reliable compared to German equipment. The Shermans worked. They didn't require constant specialized attention. They didn't strand their crews with mysterious failures that required expert diagnosis. They simply functioned reliably, day after day, battle after battle. The fate of the abandoned Panzer IV that Sergeant Harrison found near Sbeitla encapsulated the entire story. Superior combat capabilities, sophisticated engineering, impressive specifications, all rendered meaningless by a transmission failure that occurred at the worst possible moment, forcing the crew to abandon their tank and flee on foot. That single vehicle represented thousands of similar failures across all theatres where German armour fought. Each breakdown reduced effective German combat power. Each lost tank represented industrial capacity Germany couldn't afford to waste. Each abandoned vehicle provided intelligence to enemies who learned how to exploit German weaknesses. The American examination of that particular Panzer IV, and dozens of others captured during the Tunisia campaign, revealed truths that shaped the outcome of the war in ways that extended far beyond the North African theatre. Industrial warfare demanded vehicles that worked reliably under sustained operations. Sophisticated engineering that couldn't be maintained under field conditions produced expensive failures rather than effective weapons. Simple, robust design that could be serviced by ordinary soldiers using basic tools proved far more effective in practice than theoretical perfection that required specialists and specialized equipment. These lessons, learned through meticulous examination of enemy equipment and confirmed by combat experience, became foundational principles of American military vehicle development. The abandoned Panzer IVs of Tunisia taught American engineers and commanders that in armored warfare, as in most aspects of military operations, The weapon that functions when needed beats the weapon that might be theoretically superior if it could only reach the battlefield and complete its mission. Reliability and maintainability weren't secondary considerations. They were the foundation upon which combat effectiveness was built. The Panzer IV remains famous today as one of Germany's most successful tank designs, serving from 1939 through 1945 in every theatre where German forces fought. Production totals exceeded any other German tank design. Combat records documented impressive capabilities. But the maintenance reality told a different story, one of sophisticated machines that required more support than combat conditions could provide. That gap between design ambition and operational reality helped determine the outcome of armoured warfare in World War II, favouring Allied forces that fielded mechanically simpler vehicles designed to be maintained by ordinary soldiers under extraordinary circumstances. The summer of 1943 brought systematic evaluation of German armoured vehicles at multiple American facilities. Aberdeen Proving Ground received the largest collection of captured equipment, but smaller evaluation teams operated wherever significant numbers of enemy vehicles could be examined. Each team documented findings that built a comprehensive picture of German strengths and weaknesses. The Panzer IV transmission analysis formed just one part of a broader assessment, but it carried disproportionate weight because it explained so much about German operational difficulties. Technical intelligence officers compared German and American maintenance philosophies through detailed case studies. They documented specific repair procedures on both Sherman and Panzer IV tanks, timing each step, noting tools required, and assessing skill levels necessary to complete the work successfully. The results were compiled into comparative analyses that circulated through Army maintenance commands and influenced training programs. One particularly revealing comparison examined track replacement procedures. Both tanks used steel tracks that wore out over time and required periodic replacement. The Sherman used a track design with detachable end connectors that could be removed with standard tools. A trained crew of 5 could remove and replace an entire track in approximately 2 hours without specialized equipment. The process was straightforward enough that tank commanders could supervise their own crews performing the work without requiring outside assistance. The Panzer IV used a more complex track design with pins that had to be driven out and hammered back in for reassembly. The process required track jacks to support the weight during removal, specialty hammers and punches to drive the pins, and considerable physical strength to manipulate the heavy track sections. A complete track replacement took 4 to 6 hours with experienced personnel and proper equipment. Under field conditions without ideal tools, the job could stretch to 8 hours or more. Worse, the process was physically demanding enough that crew members already exhausted from combat operations struggled to complete it without assistance from maintenance personnel. The disparity extended to virtually every maintenance task: oil changes, air filter service, spark plug replacement, brake adjustment. Every job took longer on the Panzer IV and required more specialized knowledge. American mechanics examining captured tanks compiled lists of special tools needed for German maintenance procedures. The lists ran to dozens of items, many of which had no American equivalents. By contrast, Sherman maintenance could be accomplished with standard automotive tools that any decent motor pool already possessed. The electrical system comparison revealed another philosophical difference. Sherman electrical systems used 12-volt components common in American automotive applications. Parts were readily available, interchangeable across different manufacturers, and familiar to anyone who had worked on civilian vehicles. The Panzer IV used a 12-volt system as well, but German components weren't standardized the same way. A generator from one manufacturer might not directly replace a unit from another factory without modification. Wiring harnesses used different color codes. Connectors varied between production batches. German quality control maintained high standards for individual components, but system-level interchangeability suffered from lack of true standardization. Each tank was essentially hand-fitted during assembly, with mechanics adjusting components to make everything work together properly. This approach produced well-built tanks when construction occurred under factory conditions with skilled workers and unlimited time. But it created nightmares for field maintenance where parts had to be swapped quickly without extensive fitting and adjustment. The fuel system provided yet another example of different design approaches. Sherman fuel tanks were simple sheet metal structures with straightforward plumbing. Fuel filters were accessible from outside the tank. The fuel pump was a standard automotive component that could be replaced in minutes. The entire fuel system was designed around the assumption that soldiers with basic mechanical knowledge would need to service it under less than ideal conditions. The Panzer IV fuel system incorporated more sophisticated features intended to ensure reliable fuel delivery under any operating condition. Multiple filters at different points in the system. Auxiliary pumps for cold weather starting. Vapor separators to prevent fuel starvation at extreme angles. Each component represented sound engineering solving real problems, but the complexity meant more components that could fail, more connections that could leak, and more specialized knowledge required for troubleshooting and repair. American ordnance officers noted that German engineering tended to solve problems by adding components and complexity. American engineering tended to solve problems by simplifying designs and eliminating potential failure points. Both approaches worked, but they produced very different results when equipment had to be maintained under combat conditions by tired soldiers using whatever tools they could find. The weapons systems on both tanks showed similar contrasts. The Sherman's 75mm M3 gun was a straightforward design adapted from existing anti-aircraft artillery. The recoil mechanism was robust and reliable. The mounting allowed for relatively easy removal and replacement if needed. Maintenance consisted primarily of cleaning and lubrication, tasks any crew could perform. The fire control system, while not as sophisticated as German equivalents, was simple enough that repairs could be accomplished with basic skills. The Panzer IV's 75mm Quake 40L-43 gun represented more advanced engineering. The recoil mechanism was more compact and sophisticated. The mounting incorporated features that improved accuracy. The sighting system provided better target acquisition capabilities. All of these advantages came at a cost in complexity. The recoil mechanism required periodic disassembly and service that Sherman mechanisms avoided through simpler, more robust design. The mounting included more adjustment points that needed periodic checking. The sighting system, while superior when properly maintained, required specialized knowledge to calibrate and repair. German tank commanders interviewed after the war frequently praised their guns' capabilities while expressing frustration with maintenance requirements. The guns worked wonderfully when properly serviced, but proper service required time and expertise that combat operations rarely provided. Sighting systems fell out of calibration. Recoil mechanisms developed leaks. Elevation mechanisms required constant adjustment. Each problem reduced combat effectiveness until proper maintenance could be accomplished. By contrast, Sherman commanders reported that their guns simply worked. They weren't as accurate at extreme ranges. They didn't have quite the penetration of German weapons, but they functioned reliably, battle after battle, with minimal maintenance beyond basic cleaning and lubrication. In sustained combat operations, reliability proved more valuable than theoretical perfection that couldn't be maintained. The armor protection on both tanks followed different philosophies as well. The Panzer IV used face-hardened armor plate that provided excellent protection for its thickness. The manufacturing process that created face-hardened armor was complex and time-consuming, but it produced armor that resisted penetration better than softer steel of similar thickness. When hit, face-hardened armor often deflected or shattered projectiles that would have penetrated softer plate. This superior ballistic protection came at a cost. Face-hardened armor was brittle. When it failed, it tended to crack and spall, sending fragments through the crew compartment. Welding repairs were difficult because the heat treatment made the steel hard to work with. Combat damage that would have been repairable on softer armor often meant replacing entire plates on face-hardened vehicles. The Sherman used rolled homogeneous armor that was softer than face-hardened plate, but more ductile. For a given thickness, it provided somewhat less protection against penetration. but when hit, it deformed rather than shattering. Sparling was less severe. Most importantly, rolled homogeneous armour could be welded and repaired relatively easily under field conditions. Battle damage that would have required factory-level work on. A Panzer IV could often be repaired by battalion maintenance sections on a Sherman. This meant damaged Shermans returned to action faster and more reliably than damaged German tanks. The reality of armoured warfare was that vehicles got hit. Armour didn't prevent damage. It reduced damage and protected crews. But every tank fighting for any length of time accumulated hits that degraded its protection. Being able to repair that damage and return the vehicle to combat operations mattered enormously. German tanks, with their superior face-hardened armour, often couldn't be repaired adequately in field conditions. American tanks, with their more repairable rolled homogeneous armour, could be patched up and sent back into battle. Aberdeen Proving Ground conducted live fire tests against captured Panzer IV armour to document penetration characteristics and damage patterns. The tests confirmed that face-hardened armour provided excellent protection when intact, but created severe crew casualties. Penetrated. The brittle armour shattered into fragments that caused horrific wounds. By comparison, Sherman armour, when penetrated, tended to produce cleaner holes with less fragmentation. Neither situation was good for the crew, obviously. But the difference in wounding patterns was significant enough that American armour designers continued to specify rolled homogeneous armour despite its slightly inferior ballistic protection. The turret design on both tanks reflected different priorities as well. The Panzer IV turret was relatively compact, with minimal wasted space. Every cubic centimetre was utilised efficiently. This made for a cramped working environment but reduced the target size and weight. The turret ring diameter was relatively small, which limited growth potential. German designers hadn't anticipated the need to mount larger guns later in the tank's service life. When 75mm guns replaced earlier 50mm weapons, fitting the larger gun required extensive redesign. The Sherman turret was more spacious, with room for crew members to work without constant interference with each other. The turret ring diameter was generous, allowing for future growth. When the British mounted their 17-pounder anti-tank gun in Sherman turrets to create the Firefly variant, the installation required modifications but was fundamentally feasible because adequate space existed. American designers had deliberately overbuilt the turret to allow for upgrades they anticipated would be necessary as the war progressed. This design approach, building in margins for future growth, was characteristically American. Commercial automotive manufacturers had learned through experience that products needed room for improvement and modification. A truck chassis that could only accommodate one specific body configuration had limited market appeal. A chassis designed with generous load capacity and mounting points could be adapted to dozens of uses. Sherman, designers applied the same thinking. Build the basic vehicle with enough margin that future improvements could be incorporated without complete redesign. German designers tended to optimize each component for its specific purpose at the time of design. This produced elegant engineering solutions but limited flexibility. The Panzer IV was never designed to mount a gun larger than 75mm. The turret couldn't accommodate anything bigger without fundamental redesign. By contrast, Sherman turrets accommodated 76mm guns with only modest modifications. The British 17-pounder, an even larger weapon, required more extensive changes but was still feasible. The generous margins American designers had built in proved invaluable, as combat experience revealed the need for better firepower. The suspension systems on both tanks used different approaches that reflected broader design philosophies. The Panzer IV employed leaf springs, a time-tested suspension design used on trucks and older tanks. Leaf springs were relatively simple, required minimal maintenance, and provided adequate performance for a 25-ton vehicle. The weakness was limited travel, which meant the tank rode roughly over broken terrain. But the design was proven and reliable when properly maintained. The Sherman used vertical volute spring suspension, a more complex system that provided better ride quality and improved cross-country mobility. Each bogey unit contained springs and shock absorbers that provided longer suspension travel than leaf springs. The improved ride reduced crew fatigue and allowed faster movement over rough terrain. The cost was more complex maintenance requirements and more components that could fail. American designers judged that the mobility advantages outweighed the increased maintenance burden, especially since the suspension could be serviced from outside the vehicle using standard tools. Testing at Aberdeen confirmed that Sherman suspension provided superior cross-country performance. The longer suspension travel meant the tank could traverse obstacles that would jar a Panzer IV severely. The improved ride meant crews arrived at battles less exhausted. The Sherman could sustain higher speeds over rough terrain without excessive wear on components. All of these advantages contributed to operational effectiveness in ways that raw specifications didn't capture, but the maintenance accessibility proved equally important. Bogey units on both tanks required periodic service. On the Sherman, mechanics could access and service each bogey unit from outside, removing and replacing units as needed without extensive disassembly. On the Panzer IV, accessing suspension components often required removing side skirts and sections of track, turning a simple job into a major undertaking. Field maintenance reports documented that Sherman suspension could be serviced quickly and easily, while Panzer IV suspension work consumed hours that combat operations rarely allowed. The engine compartment layout highlighted another fundamental difference in design approach. The Sherman's engine sat in the rear of the hull, separated from the crew compartment by a firewall. The engine deck could be opened from above, providing excellent access to all major components. Mechanics could stand beside the tank and reach down into the engine compartment to work on virtually any system. Oil changes, coolant service, belt replacement, spark plug changes. Every common maintenance task could be performed from above without removing major components. The Panzer IV's engine also sat in the rear compartment, but access was more restricted. The engine deck was lower and provided less working room. Many maintenance tasks required removing side panels or crawling underneath the vehicle. Oil changes meant crawling under the tank to reach drain plugs. Air filter service required removing panels and working in cramped spaces. Every routine maintenance task took longer and required more awkward positions than equivalent Sherman maintenance. American automotive engineers who examined the Panzer IV noted that German designers seemed to prioritize compact packaging over maintenance accessibility. Every component fit precisely into available space with minimal clearance. This made for an efficient design from a packaging standpoint, but created difficulties for mechanics who had to service those tightly packaged components. American designers, trained in an industry where maintenance costs determined profitability, built in generous clearances and access points, even if it made the vehicle slightly larger. The driver's position in both tanks reflected different priorities. The Panzer IV driver sat in the left front hull with adequate but not generous space. The controls were mechanically simple: steering levers, clutch pedal, brake pedal, throttle. Everything a driver needed was present and functional, but the ergonomics showed little consideration for operator comfort. The seat was basic. The vision devices were adequate but not exceptional. Everything worked, but little thought seemed given to reducing driver fatigue or improving situational awareness. The Sherman driver's position was more spacious, with better ergonomics. The seat provided more support. The controls were arranged for easier operation with less physical effort required. The vision devices provided better situational awareness. These improvements didn't make the Sherman dramatically better in any single category, but they reduced driver fatigue and made it easier to operate the tank effectively over extended periods. In sustained combat operations, these apparently minor improvements accumulated into significant advantages. The same pattern appeared throughout both vehicles. German design focused on performance specifications and efficient packaging. American design focused on operational effectiveness and maintainability. Neither approach was inherently wrong. They simply reflected different priorities based on different assumptions about how tanks would be used and supported. German armoured doctrine assumed that panzer units would operate with extensive support from specialised maintenance companies. Highly trained mechanics with proper tools and equipment would handle any repairs beyond basic crew-level maintenance. This assumption worked reasonably well during the early war years, when German forces operated from prepared bases with established supply lines. It failed catastrophically when operations extended into Russia with vast distances, primitive roads, and disrupted logistics. Suddenly, German tanks needed maintenance support that didn't exist. Vehicles broke down and couldn't be repaired because the specialized support German designers had assumed would always be available simply wasn't there. American armored doctrine assumed that tanks would operate far from major support facilities and would need to be maintained by their crews, using whatever resources were available. Designers built tanks that could be serviced with basic tools by soldiers with basic mechanical knowledge. This assumption proved correct across all theatres where American armour fought. From the deserts of North Africa to the bocage of Normandy to the jungles of the Pacific, Sherman crews kept their tanks running under conditions that would have immobilized German equipment. The strategic implications became clear to American military planners as data accumulated from multiple sources. Combat reports from Tunisia, technical intelligence analyses from Aberdeen, after-action reviews from maintenance battalions. Every source confirmed the same basic conclusion. German tanks, while impressive in many specifications, couldn't maintain sustained operations because their maintenance requirements exceeded what combat conditions could support. This reality shaped Allied strategy going forward. American commanders knew they held an advantage in operational sustainability that complemented their numerical superiority. German tanks might win individual engagements through superior firepower and armour, but Allied tanks would win campaigns through sustained presence and consistent operational availability. A panzer unit at 50% operational readiness on its best day couldn't match a Sherman unit at 75% operational readiness sustained week after week through continuous operations. The Tunisia campaign provided the first large-scale validation of these principles. German forces in North Africa fielded some of the finest armoured units in the Wehrmacht, equipped with the latest tank variants, and commanded by experienced officers who understood armoured warfare as well as anyone in the world. Yet they lost, not because their tactics were inferior, not because their equipment was individually inferior. They lost because they couldn't maintain enough tanks in operational condition to sustain continuous operations against numerically superior Allied forces that kept their equipment running reliably. Field Marshal Erwin Rommel himself acknowledged maintenance problems as one of the critical factors limiting German effectiveness in North Africa. His forces couldn't sustain operations because vehicles broke down faster than they could be repaired. Supply difficulties compounded the problem, but even when parts were available, the specialized maintenance required to keep German equipment operational simply couldn't be accomplished under field conditions with available resources. By May 1943, when the last Axis forces in Tunisia surrendered, over 250,000 German and Italian personnel entered captivity. Hundreds of tanks, trucks, and other vehicles fell into Allied hands. The captured equipment provided an intelligence windfall that would influence Allied operations for the rest of the war. But the most important lessons weren't about specific technical capabilities. They were about fundamental design philosophy and the critical importance of maintainability. American armor doctrine evolved to emphasize integrated logistics as a core component of combat power. Maintenance companies received enhanced training and equipment. Supply systems developed to ensure parts availability at forward locations. Recovery procedures improved to minimize vehicle losses due to abandonment. Every aspect of armored operations incorporated lessons learned from examining why German forces failed despite their technical sophistication. The Panzer IV itself continued evolving after Tunisia. Later variants incorporated additional improvements, attempting to keep pace with increasingly capable Allied armor. The Ausf H model, introduced in April 1943, added even thicker armor and minor improvements. The final Ausf G variant, produced from June 1944 through the end of the war, stripped away electric turret traverse and other features to simplify production as Germany's industrial situation deteriorated. But none of these modifications addressed the fundamental maintenance issues that plagued German armour throughout the war. German engineers understood the problems. Field reports documented maintenance difficulties in exhaustive detail, but solving those problems would have required complete redesign of vehicles already in production, something Germany's industrial situation wouldn't permit. Factories struggled to maintain production rates with increasingly limited resources and constant disruption from Allied bombing. Redesigning existing vehicles to improve maintainability wasn't feasible when simply maintaining current production levels consumed all available capacity. The Sherman, by contrast, underwent continuous improvement throughout its production life. Early models gave way to improved variants with better engines, upgraded suspensions, and enhanced armour. The M4, a 3, with its Ford GAA Vate engine represented the pinnacle of Sherman development, combining excellent reliability with improved performance. But even early model Shermans remained effective because their fundamental design philosophy emphasized maintainability and operational sustainability. Post-war analysis by both American and German military historians confirmed what combat experience had demonstrated. In armored warfare, sustained operational capability mattered more than momentary superiority in individual specifications. The most powerful gun was worthless if the tank couldn't reach the battlefield. The thickest armour provided no protection if the tank was deadlined awaiting maintenance. Sophisticated engineering meant nothing if field mechanics couldn't keep the vehicle running. These lessons shaped American military vehicle development for decades. The M48 Patton tank incorporated maintainability as a design requirement from the beginning. The M60 that followed emphasized reliability alongside performance. The Mohn Abrams, despite its radically different turbine engine and advanced systems, maintained the principle that ordinary soldiers must be able to maintain it under field conditions using available resources. German post-war tank development, ironically, adopted many principles that German wartime design had neglected. The Leopard 1 main battle tank, developed in the 1960s for the new West German Bundeswehr, emphasized reliability and maintainability as core requirements. Designers consciously applied lessons learned from wartime experience, creating a tank that could be maintained by conscript soldiers with limited training rather than requiring specialists. The Leopard 1 became one of the most successful tank designs of the Cold War era, serving with numerous armies and remaining in production for decades. The captured Panzer IVs that taught American engineers so much about maintenance philosophy eventually left, Aberdeen proving ground for museums and collectors. Some survive today as historical artifacts, testament to German engineering capability and reminders of lessons learned through hard experience. But their greatest contribution wasn't as museum pieces. It was as teachers, showing American engineers and commanders what not to do when designing and operating armoured vehicles. The maintenance revelation that began with Sergeant Harrison discovering an abandoned Panzer IV beside a Tunisian road in February 1943 rippled through American armoured forces and influenced strategy, tactics, doctrine, and equipment development. The simple fact that replacing a Panzer IV transmission took all day, while replacing a Sherman powertrain took 2 hours, encapsulated a broader truth about industrial warfare. Success depended not just on building powerful weapons, but on building weapons that could be sustained in operation under the brutal conditions of sustained combat. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.